Hi, and welcome to today's lecture. We're going to cover section 7.6, which is talking about proportions and problem solving with rational expressions, of course. Now, that being said, let's jump straight into what is a proportion. A proportion is looking at two expressions, or two rational expressions, that are set equal to each other. So I have A over B is set equal to C over D. You can then say, out of this proportion, if you were to look at it as a cross multiplication, for example, this is an equation, so you can do this, that AD is equal to CB. So you're then able to take your rational expressions and make them so that they are no longer rational, but instead products. Now, this is very powerful. As you can see, we have x over 10 is equal to 5 over 9 in our first example. And if we were trying to solve for x, all we would have to do, since we are in a proportion, meaning we have one rational expression set equal to another, all we would have to do is simply cross multiply. And this would give you 9x is equal to 50. Divide by 9, x is equal to 50 divided by 9. And you might be saying, okay, well, how is this any different than what we have been doing? Or can I use cross multiplication all the time? They're both valid questions. Let's take a look. In this example, you have one fraction is set equal to another fraction. Cross multiplication works. You can absolutely do that here. If I had some other term set off to the side here, I wouldn't want to cross multiply because I'm going to lose something. So then the question then becomes, can I use the LCD to clear my fractions? And the answer is absolutely. You can always do that, providing you're in an equation. So same exact problem. If I were to look at my LCD here, my LCD is going to be 90, right? So LCD is 90. You could also say it's 9 times 10 for simplification. But you have 90. If I were to multiply 90 to both sides here, 10 goes into 90 9 times, that's 9x. 9 goes into 90 10 times, that is 5 times 10, which is also 50. And then you divide out, x is equal to 50 over 9. Exactly the same thing. You're just building in a little bit of an extra step there. However, canceling the LCD throughout the problem to cancel your fractions will be something that works even if you have additional terms. With a proportion, though, you can use that cross multiplication just as a little short technique, if you will. Let's try another example, and I have plenty of room for this. So I have x plus 1 over 2x plus 3 is in proportion with 2 over 3, or 2/3. I'm going to use the cross multiplication, and I can do that because, again, I have one fraction is set equal to another fraction. So one rational expression equal to another rational expression. I can use that cross multiplication. That will give me 3 times the x plus 1 is equal to 2 times the 2x plus 3. Simplify these. This is 3x plus 3 is equal to 4x plus 6. You're going to simplify this even further. Now, I am going to move my 3x over so that x remains positive, just a preference. I'm also going to move my 6 over, and that is a -3. So x equals -3. Now, there is one other little thing that we talked about before. Whenever you're working with equations with rational expressions, if you have a variable in that denominator anywhere within the problem, you need to check your domain because you have to see if your solution is inside of your domain set. So let's just check our domain. I have 2x plus 3 cannot equal 0. 2x cannot be -3, excuse me, and x cannot be a -3/2. So can my solution of -3 work here? Yes, absolutely. So you do still need to build in that check, like we said before. just to make sure everything is actually working. Okay, so proportions are very easy to work with in practice. So let's put a little application to them. So we're going to do some word problems now. I know they're your favorite, so here we go. The first problem that we're going to cover is a rate of work problem. And a rate of work problem is talking about portions of an hour. So you'll see what I mean in just a moment. As you follow along, please note that you have your word problem on your paper. It also gave you a table. So I will put this table up in just a moment. But let's read the word problem. Remember, first time, let it hit you in the face like a baseball bat, and then we'll tackle it. First time. Melanie and Nicole volunteer in the recycling plant. Melanie can sort a batch of recyclables in 2 hours if working alone, while her friend Nicole needs 3 hours to complete the same job. If they work together, how long will it take them to sort one batch? So here's our table so that we're ready to capture information. So we have Melanie, we have Nicole, and we have together. I'm abbreviating. You can also see this marker is getting very light. So I'm going to switch my marker to this nice blue one. Oh yeah, look at that blue. All right. Okay. Within your table, you have hours to complete the job. And then you have part of job completed in 1 hour. Okay. So let's go back through our problem and start filling in our chart. So it says Melanie and Nicole volunteer in the recycling plant. Melanie can sort one batch of recyclables in 2 hours if working alone. So Melanie can complete the job in 2 hours, where her friend Nicole needs 3 hours to complete the same job. If they work together, how long will it take them to sort one batch? So together, we don't know. Now, that's all the information we are given, and actually that's all the information we need. This extra column that you're seeing here is part of the job completed within 1 hour. If it takes Melanie 2 hours to complete the job, how much of the job is actually completed after 1 hour? Half, right? So that would be 1/2. How about for Nicole? Well, if it takes her 3 hours, in 1 hour she's completed 1/3 of her job. And the together time, we don't know, but it would be 1/x. So within 1 hour, they've completed 1x of the job. Now, looking at our setup, what we have are these two people working together to create this time. So you can kind of think of this, and it's not on the chart this way, but you can kind of think of this as like a double bar, meaning you're equaling your together time. So together I have 1/2 and 1/3 makes up my time of 1/x. Excellent, so now I have an equation to work with. Looking at my equation, I have fractions. It's inevitable. So what we're going to do is we're going to clear our fractions out with an LCD, which is 6x. That leaves me 3x here, plus 2x is equal to 6. Combining my terms, that is 5x is equal to 6, or x is equal to 6/5. Now we're talking about time. We don't usually like to say 6/5 hours. So instead, it would be more appropriate to say 1.2 hours if you're using decimal. Or you could also say 1 1/5 hours. Both of these would be more appropriate, but all of these are still accurate. So you can use any one of those 3 possible solutions. But in discussion, you would probably use one of these 2 formatted answers. And that's it. Now, Remember what I said before? You do want to check to make sure that you're in your domain. I know that x is down here. That means I cannot divide by 0. So x cannot be 0. And this answer is definitely not 0. So we are good. And that's true of most application problems, but it's still good to check. Okay, let's try another one. We're going to do another work problem. Work problem. That way we can go through and get some practice on it. First time, one custodian cleans a suite of offices in 3 hours. When a second worker is asked to join the regular custodian, the job only takes 1.5 hours. How long does it take the second worker to do the same job, to do the job alone? So here's what we're going to do. I have a table that's already provided for you, so we are going to work on that. We have our first custodian. We have our second custodian. We have a together time. So the hours to complete the job and the part of the job in 1 hour. So reading it again, one custodian cleans a suite of offices in 3 hours. When a second worker is asked to join the regular custodian, the job only takes 1.5 hours. So it's talking about both of them working together there. 1.5 or 1.5. How long does it take the second worker to do the job alone? We don't know. Let's talk about the part of the job in 1 hour time frame. So here it would be 1/3. Here it's 1/x. And here it's 1/1.5. Oh, we have decimals in fractions. So if you weren't too impressed by having fractions throughout the course or just decimals, now you get both decimals with fractions. Don't worry, it's easy to work with. All right, let's put this into an equation. So I have 1/3 plus 1/x is equal to 1/1.5. Now, there are a couple ways that you can approach this. The first is you can see that 1.5 is half of 3. That's pretty easy. And you could easily say that my LCD of the problem would be 3x. But let's say you didn't see that. Let's just say. You could technically move this decimal place over, but you have to do it up here as well. So if it helps, pencil in a little decimal there with my blue marker that's not wanting to write. There we go. And after that decimal, you'd have 1.0. So you'd have 0.0 there. If you move this decimal place one place, just like that, this, instead of having a fraction with a decimal, becomes just a fraction, which is 10/15. Some of you might think that's nicer to work with, and that's perfectly fine. Now, that being said, what is your LCD looking at this modified problem? Well, I'm seeing that this would actually be 15x. So let's take 15x and multiply my LCD to clear the fractions. That's an x. That gives me 5x plus x cancels, that's 15, is equal to 15 cancels, that's 10x. Move your 5x over. 15 is equal to 5x. Divide by 5, x is 3. We're talking about 3 hours for the second custodian. Now, keep in mind, I had an x in the denominator. I can't equal 0 here, and so this is not 0. I am good. Okay, very good. Let's try another problem. But we're going to move away from work problems because those are fairly easy. Once you get the information collected in your chart, you just simply organize it into an equation there. I am also going to try using a different marker, something that's a little darker. a little easier on the eyes. So I don't know why my notes are separated that way, but that is A-okay. We are going to keep on going. Section 7.6. I am on example number 5. So we are going to talk about some distance, rate, and time problems. We've worked with these in the past. So just as a reminder, distance is equal to rate times time. Now, you can modify this problem so that you can solve for other variables. So if you're solving for r, for example, you would divide by that t. So you'd have distance divided by time. If you're solving for t, your time would be the distance divided by the rate. And so all three of these work together. They're interchangeable because when you're looking at an equation, remember you're balanced on either side. Now, that being said, let's go into our first problem. There is a chart here, so I'm just going to capture this chart really quick. And it says truck and car. Might help if I write them in order. Truck, car. Now it sets up your columns. It doesn't actually have any headers for your columns, but I always set mine up as distance, rate, and time. It's just easier that way to capture my information. Let's read through the problem. A car travels 180 miles in the same time that a truck travels 120 miles. If the car's speed is 20 miles per hour faster than the truck's, find the car speed and the truck speed. Okay, that was the first time. Second time, let's pull out some information. A car travels 180 miles in the same time that a truck travels 120 miles. I also know my time is the same, so I'm putting that in here. If the car's speed is 20 miles per hour faster than the truck, question, how fast is the truck? We don't know. But the car is 20 miles per hour faster. So if the car's speed is 20 miles per hour faster than the truck's, find the car speed and the truck speed. Okay, so I've captured all of my information. Now I need to get some equations. Now, keep in mind, what am I actually interested in for this problem? I'm looking for the speed. That is the question that I have on hand. So I'm going to solve my equations, or get my equations rather, for time. So I'm going to use this pre-formatted version of distance, rate, and time. So this time is talking about 120 divided by r. This time is talking about 180 divided by r plus 20. I know my time is the same because it mentioned it in the problem, and these are both t. So I can say that I have 120 divided by r is equal to 180 divided by r plus 20. Hey, look at that. It looks like I have a proportion. Cool. And it's only in one variable. So at this point, I could actually solve pretty easily by cross multiplying. So at this point, I've got my equation set up. I'm going to cross multiply. Gives me 120 times r plus 20 is equal to 180 r. At this point, you need to distribute. So you have 120 r plus that's 2400 is equal to 180 r. I'm going to move my 120 over. So that's 2400 is equal to 60 r. R will equal, once you divide out 60, R will equal 40, which is 40 miles per hour for the truck. The truck is 40 miles per hour. And it was asking for the car speed and the truck speed, so I have the truck. The car is 40 plus 20, which is 60 miles per hour. Okay, very good. Very easy to do. Now, let's try going through another problem. Get some board space. Awesome. Let's go into example number 7. Another distance, rate, and time problem. I am getting all of my board space back. And now we are talking about a plane. So a plane flies 630 miles with the tailwind of 35 miles per hour. Against the wind, he flies only 455 miles in the same amount of time. Find the rate of the plane in still air. So this one's a little different than what we've had in the past. So let's look at that table that they give us. There is a header for with the wind, and there's a header for against the wind. Great song. Okay, so that being said, we have our table set up. I'm going to put my headers as distance, rate, and time. Let's read it one more time. It says a plane flies 630 miles with the tailwind of 35 miles per hour. So 630 miles now with the tailwind. If I were to say that the tailwind is 35 miles per hour, that is talking about wind that is pushing the plane. So tailwind is always pushing behind the plane, thus increasing the plane's speed. So if I'm looking at just the speed of the plane, I don't know what that is. It doesn't tell me. It says basically R. But I have a tailwind of 35 miles per hour, so that would be R plus 35. Okay. Against the wind, he flies only 455 miles in the same amount of time. So I know my time is the same. That's very clear. Now, let's talk about that speed. The speed here is going to be R, the speed of the plane in still air, but minus 35. How do I know it's minus 35? It didn't say it in the problem, did it? But it did. You're flying against the wind. So remember, a tailwind is pushing the plane in the same direction, but a headwind is pushing against the plane, slowing it down. So we now have our table set up. We have all of our information. And let's just go ahead and solve these so that I have equations of t. So t is equal to 630 over r plus 35. T is equal to 455 divided by r minus 35. And I know my time is the same, so I can set those equal. Just like so. And now I can look at it and say, okay, I'm looking for the speed of the plane in still air, or the rate of the plane in still air. And I am solving for r here, so that's great. I already know I'm on the right track. I have a proportion. Let's go ahead and cross multiply and solve this baby. So I have 630 times that r minus 35 is equal to 455 times r plus 35. Okay. Now, at this point, I highly suggest utilizing a calculator if you have one in front of you, but these numbers are going to get pretty large. So 630, I'm going to distribute, that's 630R minus, this is going to be 22,050, so 22050. Distribute on this side, that's 455R, plus this one's going to be 15,925. Like I said, big numbers, use a calculator. Okay, at this point, I'm going to move my 22,050 over. I'm going to move my 455 over. On this side, I get 175R. On that side, I get 37,975. Once you divide by 175, you should get the rate as 217 miles per hour. And because I'm looking for the rate of the plane in still air, I'm talking about just the R value. I'm not talking about with the wind or against the wind. So I'm looking at just that R value. which is 217 miles per hour. Excellent. So let's try that next problem. So distance, rate, and time problems are always fun because, remember, you have one equation technically, distance is equal to rate times time, but you can kind of manipulate it based off of the variables you're trying to solve for. So here we solved our equations for t, and then we got a proportion we solved for r directly, and that was very nice. So you can always try to manipulate your problems. I'm going to do that in this next two problem set. So question number 8 is, suppose two trains leave a station at the same time, traveling opposite directions. One train travels 10 miles per hour faster than the other. In 4.5 hours, the trains are 414 miles apart. Find the speed of each train. First time, get your table up so you know you have distance, rate, and time. You're talking about two trains, so train 1, train 2. Suppose two trains leave a station at the same time, traveling opposite directions. One train travels 10 miles per hour faster than the other. Question, how fast is the first train? I don't know, that's R. But the other train is 10 miles per hour faster, so that's R plus 10. In 4.5 hours, they left at the same time, they've traveled 4.5 hours each. In 4.5 hours, the trains are 414 miles apart. Question, how far did the first train travel? D, I don't know. How far did the second train travel? Remember, this is a total distance. We've talked about this before. This is 414 minus D, because you're looking at the difference of the total distance from what this train has traveled. Okay, very good. 4.5 hours, trains are 414 miles apart. Find the speed of each train. Okay, so let's get some equations. And I'm going to just say D is equal to 4.5 R here. And 414 minus D is equal to 4.5 times R plus 10. And now you might be saying, well, we've done that before. Why doesn't that look different? Well, I'm solving for the rate here. I don't know my distance values. That's where my other variable is. So I'm going to take this and just plug it in. So I have 414 minus 4.5 R is equal to, I'm going to distribute this at the same time. That's 4.5 R plus 45. Move your terms over. So this is going to be 414 minus 45 is 369. Add this over, that's 9R. Dividing by 9R comes out to 41, meaning 41 miles per hour. Now it does say, find the speed of each train. So make sure you're doing that interpretation component. So at this point, I have the speed of train 1. Train 2 is R plus 10, which is 51 miles per hour. So I have the speed of both trains at this point. All right. Wow, we're on the last problem already. That was fast. Okay, let's do one more. Question number 9, it's talking about hikers. Two hikers are 14 miles apart and walking towards each other. They meet in 2 hours. Find the rate of each hiker if one walks 1.8 miles per hour faster than the other. So I have two hikers, they're walking towards each other, and we're saying that in 2 hours they meet. So I have a distance, rate, and time problem. Get my distance, rate, and time chart. I have hiker 1, hiker 2. Two hikers are 14 miles apart and walking towards each other. Stop. How far did hiker 1 walk? I don't know. D. How far did hiker 2 walk? I don't know, but it's 14 miles minus d, because it's talking about a total distance here. They meet in 2 hours, so the time is 2 hours. Find the rate of each hiker if one hiker walks 1.8 miles per hour faster than the other. How fast was the first guy? I don't know, R. How fast was the second guy? 1.8 miles per hour faster. So that's R plus 1.8. Great. Let's get some equations. I have distance is equal to 2R here. I have 14 minus D is equal to 2R plus 1.8. I am interested in the rate, so find the rate of each hiker. So I am going to plug this value in for D. It's 14 minus 2R is equal to 2R plus 3.6, so I'm distributing at the same time here. Adding my 2R, that gives me 4R on this side. Moving my 3.6 at the same time gives me 10.4. Dividing by 4, I have R. On this side, I get 2.6. That's 2.6 miles per hour to write that unit in. Now, I found this rate of the first hiker. The question is, find the rate of each hiker. So I need the second one as well. That's R plus 1.8. So 2.6 plus 1.8 gives you 4.4 miles per hour. That is it. Okay, so ladies and gents, that is it for section 7.6. A lot of it was word problems, but you are working with proportions as well, especially those in application with the word problems. Okay, so stay tuned. I have another lecture coming right up.